Question 2. Chlorine reacts with many elements and compounds to form chlorides. Table 2.1 shows the information about some chlorides of period 3 elements. Formula of the chloride, of course, this one is going to be sodium chloride. Remember, this one is in group 1. So chlorides, we know them. It is just like that. They need one electron to have the full octet. Okay. So sodium is in group 1. So it also has, it loses that one electron. Then these ones balance. And then we have this. Then magnesium is in group 2. So it has 2 plus. Okay. It loses the 2 electrons. And then chlorines, remember it is -1. So we must get 2 of them. Okay, 2 negatives to balance the 2 plus there. Okay, so that means we shall write MgCl2, as simple as that. Then silicon is in group 4. So this one has to be 4 plus. And then chlorine, these ones have to be 4 of them to balance this plus here, 4 plus. So we shall have silicon 4 chloride. Then the structure of the chloride, is it giant or simple? Of course, for sodium chloride, it is giant. Magnesium, this is an ionic compound. So that one is also going to be giant. Okay. And then for silicon chloride, this one is simple. Okay. It has covalent bonding. They even gave us the bonding. Simple covalent bonds. Okay. Then pH of the solution. No, wait. Bonding in the chloride, this one is ionic. Sodium chloride. It's between metals and non-metals. Okay. Now for silicon, silicon is a metalloid. It has characters of metals at a smaller percentage, but more of non-metal. Okay. So there is sharing of electrons with the silicon here. That's why the bonding is what? More of covalent. And then magnesium, metal and a non-metal, that one has to be ionic. And then pH of the solution formed on addition of the chloride to water. For sodium chloride, that one is 7. It is neutral. Okay? When you add salt to water, the water doesn't change its pH. This one, they have said 6.2. This one, when it dissolves, magnesium, because it has a stronger charge, and then it has a smaller radius, it is going to have a high charge density. Okay. Now the water molecules here, this one is going to take the OH here. Okay. And then they will release some hydrogen ions. And then when you see hydrogen ions in solution, then that means we are getting an acidic solution. Then another thing we also know is that the hydroxides of group 2 elements, the solubility of hydroxides of group 2 elements increases down the group. So the magnesium hydroxide, which is formed here, is less soluble. Okay, it is more of a solid. You see that white PPT being formed within there. Okay, so it releases very few hydrogen ions in there. That is why you are seeing the pH is below 7. Okay. Then this other one here, silicon, of course, we know silicon at room temperature, silicon 4 chloride is a liquid. Okay. So this one with water, it actually hydrolyzes. Then it forms this insoluble salt, this insoluble solid here, silicon oxide, then plus the Mr. fumes, the HCl. To balance this, I will put a 4, and then hydrogens are 4, so I'll put a 2 here, and then oxygen becomes, the ones of oxygen also become 2. So because of this HCl, which is a strong acid, it's a strong mineral acid, I can put my pH maybe 1, or I can put 2, but the range has to be from, let's say, 1 to 3 or 4. Okay, that has to be the range. But when you are writing in the exam, don't say 1 to 4. No, just pick a figure in between the two. I mean, in between this interval. Then part B, when chlorine reacts with cold sodium hydroxide, aqueous, chlorine is both oxidized and reduced. That means this is a disproportionation reaction. Okay, the products are chlorine, water, and G. State the type of redox reaction in which the same species is both oxidized and reduced. It is what I've just talked about. This is what we call a disproportionation reaction. Disproportionation reaction. Mark these spellings. Identify G. So, to identify G with cold, of course, it is going to be sodium chlorate 1. Sodium chlorate 1. You can write it as a formula here. And by the way, if this is the capital and chlorine is another element, make sure that they lie on the same line there. Okay, so something like that. And by the way, okay, the name, let me put the name here, sodium chlorate 1. Chlorate 1. You can put the name or you can write this one here. The reaction is actually sodium hydroxide, then plus chlorine. You get sodium chloride, you get water, and then this sodium chlorate 1. So to balance, we shall put a 2 here because these are 2 sodiums. And then chlorine, this is 1, 1, these are 2. Then oxygen, we are seeing 1, 2. So we balanced already here. Hydrogen is also 2 and is also 2. So that is the equation here. When chlorine reacts with cold, aqueous sodium hydroxide. Write an equation for the reaction between chlorine and then hot. So chlorine with hot, we shall have our chlorine here plus sodium hydroxide, hot. There are 2 products that you must know that are common. We have this one and the water for both of them. So we shall have sodium chloride, then we have also water, and then we shall also have sodium perchlorate. So sodium perchlorate, ClO3. So to balance this one, I can put, let's say, a 3 here, then oxygen now becomes 6. If oxygen is 6 and then I put a 6 here to balance it, then sodium is 6. If sodium is 6 there, by the way, hydrogen is also balanced now, 6 and then 6. Then sodium must be, sodium is also 6, so if we put a 5 here, and then this will be 5, then plus 1, that will be 6. Then chlorine is also 6, so we shall put a 3 here. So that will be the equation. Remember, it has to be balanced. If the equation is not balanced, then there is no way you're going to get it correct. Okay. Roman 4, describe fully what is observed when silver nitrate, aqueous silver nitrate, is added to an aqueous solution of chloride of sodium, followed by the dilute ammonia. Now, chlorides dissolve in ammonia. Okay. Chlorides dissolve in ammonia. So, first of all, we are going to form the white precipitate. There is going to be a white precipitate. Dissolves in dilute ammonia. Okay. The white precipitate is silver chloride. This is the white precipitate. One thing you need to know is that we have chlorides, we have bromides, we have iodides. Okay, so in concentrated, we have dilute ammonia, and then we have concentrated ammonia solution. Now, chlorides, they dissolve. Okay, let me say dissolves. And then the bromide in dilute ammonia is sparingly soluble. Okay, sparingly soluble. Sometimes they even say insoluble, because something that is sparingly soluble, it forms a PPT. Okay, it forms a precipitate. And then in concentrated ammonia, it is soluble. They are soluble. Okay. Then iodides are insoluble whether it is concentrated or dilute ammonia. So this is one table you need to know for group 17. Very examinable. So keep it in mind. Part C, an excess of chlorine reacts with phosphorus to form phosphorus pentachloride. Phosphorus pentachloride is a simple molecule in the gas phase. It also exists as a solid. It also exists in a solid form as two ions. We have this one and this one here. Complete this table to identify the shapes of these species. Now, this one here, PCl5, it looks like this. We have, let me draw it here, phosphorus. Then we have, horizontally, we form something like this, a triangle. Okay, it's like a triangle. You have here, here, and there. This angle is 120, even here, 120. So better I'll put it like this. Then there is a chlorine here, 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 and then here. This is 120, 120, 120. Then, since this one is vertical and this one is horizontal, the angle in between them is what? 90 degrees. And of course, the angle between this and this is 180. So there is a pyramid up here and then the one down. So we call this one trigonal bipyramidal. Trigonal bipyramidal. This one is tetrahedral, and then of course this one has to be octahedral. Octahedral. 6 of them. How does that come about? We have this 1, 2, then here, and then there. So you have a chlorine here, 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 and there. The angle in between here is 90, but of course this one will be 180. Then we can put this one just up here, then we put the minus. So this is octahedral. Roman 2, PCl5 reacts with J to form phosphoric acid. Identify J and state the type of reaction. Of course, that has to be water. So J, you can put water or you write it in. You can write it as the formula like I've done here. But if they say name, strictly it has to be the name. Type of reaction, it is hydrolysis. Okay? Hydrolysis. Breaking down of a compound by addition of water. Actually, the reaction is PCl5, which is even a solid, then plus water, which is a liquid, and then we get phosphoric acid, is aqueous, and then plus these misty white fumes, misty fumes. So now these ones come off as fumes, so it has to be gaseous. Okay, white fumes. Now to balance this, of course, I will put a 5 here to balance the chlorine, okay? And then water, now hydrogen is 5 plus the 3, that is 8. So meaning here I will put a 4, and this 4 for the oxygen is also here. As simple as that. So this is the equation, okay? That leads to the formation of phosphoric acid from PCl5 reacting with water. Part D, chlorine reacts readily with propene to form K. K is 1,2-dichloropropane. Okay, this is the one here. And then we are seeing reaction 2. Then we form an alkene. Then Roman 1, complete figure 2 to show the mechanism of the reaction of chlorine with propene. All right. Now, this one here is what we call electrophilic addition reaction. Okay. So, first of all, the electrons that are in here are negatively charged. Now, chlorine here has gotten, this chlorine molecule here has gotten 2 chlorine atoms. These atoms are all electronegative. So this one keeps pulling electrons towards itself, and also this one does. So the dipoles cancel out. But now as this molecule draws closer to this molecule here, because of the negative charge here on the electrons, then this one, the electrons around it will be repelled. They are going to be repelled further away. So this one will appear to be losing electrons. So if it appears to be losing electrons, then it will attain a partial positive charge. So the electrons are pushed towards this one. So for it will appear as if it has received electrons, so it will attain a partial negative charge. Now that means there is going to be an attack on this pi system. And then that means electrons are going to flow from here. Then they will come to this chlorine here. The arrow shows where the electrons are moving from and where they are going. Then this one will break off. Then from there, we are going to have the hydrogen here. Then to the, remember there is this and this. So there are 2 of them. I'm going to put 1 here. Now, chlorine, this one is going to come to this one here. And then here we shall have this carbon here connected to this hydrogen here. Then there will be a CH3 here. So since this one has received, then this one has lost. So we shall have a plus here. Okay, that's a carbocation. Why are we taking this one here? I usually say that the rich get richer every single day. So this carbon here that has gotten many hydrogens, it is the one that receives this chlorine here, okay? Because this carbocation that is formed, I can say this is one group, this is another, so it is a secondary carbocation. It is more stable than when, let's say we have here the CH2, then CH, then CH3, then there is a chlorine that has been added onto this one. Now there is a plus here. You see, this is a primary because this is one group here. So this is a primary carbocation, which is not as stable as the secondary carbocation. You see that? So that's why we are having that one as the major intermediate here. By the way, there is a mark that is given for the intermediate, which is correctly written. Now, this one here that has broken off from here, it has received the electrons. Now it becomes fully negatively charged, and then it is going to offer its lone pairs of electrons to this one that is that has lost the electrons, and then we are going to have this one here. Roman 2, identify the reagent and conditions for reaction 2. When you check reaction 2 here, we have lost a chlorine here. So there is a carbon here, there is a carbon here, there is a hydrogen, and then there is another hydrogen here. Now, this one, when it loses the halogen, the next carbon in line, this one has a hydrogen, has to lose a hydrogen. So when it loses a hydrogen, then this one loses this one, then we form a double bond in between. You see that? Now, from a halogenoalkane to an alkene, here we see the formation of, the reagent here has to be sodium hydroxide or a strong alkali. But now the condition is it has to be in ethanol. Okay, so the reagent has to be sodium hydroxide. So we shall write sodium hydroxide. Okay, in ethanol, that is the condition. And then we also add heat to speed up the reaction. Okay, draw one repeat unit of the addition polymer that forms from L. Now, where is our L? Our L is this one here. So there is a carbon here, there is another one here. Okay, so we are going to display the two carbons that have gotten the double bond. So I'm going to have a carbon, then a double bond to this one here. Now this one has a chlorine, then the CH3. Okay, of course the other one was skeletal. So the hydrogens that are directly connected to the carbon, they are always hidden. So this one opens up like this and also opens this way. So what we are going to have is now going to be C, then this one is broken down, and then another C here, then a hydrogen, and then a hydrogen here. Then here we have a chlorine, and then here we have a CH3, and then here, this bond here opens up. We can even put these brackets just to single it out. But when you put an N here, it means it is a polymer. Okay, this one means there are many molecules of this in here. So don't put the N. They didn't say the polymer, just the repeat unit of the addition polymer. Okay, so this is the answer, not this one here. I was just showing you how it comes about.